Okay, let's try. We have a lot of material to go through, therefore I want to go. There are 4 pillars of relativistic astrophysics: supernovae, neutron stars, black holes, and GRBs. And I would like to present a new paradigm which we are developing. But before that, let me remind everybody in the audience some of the steps of the supernova, neutron star, black holes, and GRBs. Going quickly, everybody knows about the supernova since the observation of 1054, following 1054 of the Crab Nebula. The most important observation, which actually started 50 years ago, the start of relativistic astrophysics era, has been the discovery of a pulsar in the Crab Nebula and therefore of the second building block, neutron stars. The following story on black holes came just after the discovery of pulsar, when in Princeton with John Wheeler and with some, at the time, young collaborators and students, we introduced the concept of black hole. Therefore, this is the third building block. And of course, also that field has been successful. In other words, there was still on the theory the introduction that many of you know about the mass formula of the black hole. But the key point about the mass formula of the black hole for me was what later on we call the energy, the extractable energy, and the Coulomb energy and the rotational energy, which could be relatively 29% for the rotational energy and 50% of the electromagnetic energy of the black hole. And since that formula was written, my interest was to find a place in the universe where such enormous energy could be released. The Uhuru satellites was essential because for the first time was possible to measure, not only to know about neutron star, but also to measure the masses of neutron star in SENEX-3. And later on, the discovery of the black hole, the paradigm for the identification of Cygnus X1 with a black hole, and the only, the recognition of this, you know everything, but let me touch only on another point, that in 1992, some 20 years later, something additional to the result of Cygnus X1 came from the work of Mirabel and co-worker Rodriguez, showing for the first time that rotational energy could have a fundamental role, not just the mass limit of 3.2, but also the rotational energy powering the jets, and still this is a very open question. The fourth building block, the fourth building block have been the GRBs. It was epochal in San Francisco in 1974 when Herb Gursky and I organized a meeting at the AAAS. And the news about the GRB were just presented, and Armstrong came to give a fantastic lecture introducing the discovery of GRB. I was still under the effect of the expectation to find a place for applying the mass formula of the black holes. And it just happened that a young postdoc from France was visiting both Princeton and Stanford, and we wrote immediately an article assuming that the GRB were powered by quantum electrodynamics effect in Kerr-Newman geometry. We sent this paper to Phys.Rev.Let. Thibaut Damour is here with us, and we conclude, in particular, this work naturally leads to a most simple model for the explanation of the recently discovered gamma-ray burst. The only problem with the paper is that we predicted an expected energy of the order of 10 to the 54, mass of the black hole over the sun, which was absolutely not evidence to exist at the time, because nothing at the time was known about the distance of gamma-ray burst. To us, this paper was satisfactory, presenting conceptually that the GRB could be explained. And I remember asking Rashid Sunyaev, what do you think? And Rashid said, too many models. And indeed, in those days, the number of models were much, much bigger than the number of the GRBs. This is a nice picture of the time in which, in addition to Thibaut Damour and Francis, who is still with us now today, there was a fantastic man who helped us tremendously in the following work of the acceleration of the electron-positron plasma in the field of black holes, Jim Wilson, and understanding that the vacuum polarization process was not only leading to the plus-minus creation, but also to a very powerful acceleration mechanism for GRBs. Well, all of you know the rest of the part of the story, and in particular, the launching of the Compton satellite and the fact that they were divided between the short and the long GRBs. Cuveliotus was one of the leaders. Marco Tavani also was very active at the time in this differentiation between short and long. But the mystery was growing thicker and thicker. The distribution of these short and long GRBs, one less than 1 second or longer than 1 second, was just a fact, but was no real deep interpretation. I have to mention another paper, in addition to the one which I just mentioned of Mirabel for the jet and our work with Thibaut, a very interesting paper at the time, the one of Tsupiran, Narayan, and Pashinsky. In that paper, they also presented the possibility that gamma-ray bursts were extragalactic and assumed that one of the sources were binary neutron stars. Therefore, this, I think, was the situation. As far as I can understand, our emphasis on the black hole and binary neutron star from Pashinsky, Narayan, and Piran. The next step, of course, has been the great discovery made by the team of BeppoSAX. And maybe I would like to spend one word more on this. Filippo Frontera is with us today, but the community in US who was working on the gamma-ray burst were mainly the gamma-ray burst community. The gamma-ray community. Riccardo Giacconi was working on the X-ray, much lower energy. The two communities were historically not, I will not say, they were different communities. The fantastic thing of the teacher of Riccardo Giacconi Giuseppe Occhialini, was to conceive a mission mixing the X-ray community with the gamma-ray community on the same telescope. And the result was fantastic, was the discovery of the afterglow. And therefore, what it became clear is that a gamma-ray burst is not 1 second, less than 1 second and more than 1 second, but the gamma-ray bursts have an activity lasting from 10 to the, up to 10 to the 4, 10 to the 5 seconds after. And all of you know, because this has been propagandized many times, that this was the crucial step in order to identify the source. But this was continued in the following mission after with Swift and with Fermi, and finally the big saga of GRB started with the collaboration from the ground and from the Radio X, etc. You know that, but the key point was that that number that Thibault and I introduced just after the discovery of gamma-ray burst of 10 to the 54 erg finally was proved to be correct. Or at least, not only that the system were extragalactic, but that the black hole, in principle, could play an essential role. I think I would like to spend the rest of the talk emphasizing not the technological result of identifying the distance of a gamma-ray burst by the afterglow, which was enormously important, but to attract the attention to the physics of the rich physics, the incredibly rich physics, thanks to the missions that have been flying since Swift and Fermi, the physics of the afterglow. The 4 pillars of relativistic astrophysics have been, before they were separate, supernova, neutron star, black holes, GRB. Black holes forming, black hole observed, jets, they were the detached argument. But now, bit by bit, a new picture comes, the cosmic matrix. And I would like to identify, this is a personal version, of course, some of the crucial moments which have led to the introduction of the cosmic matrix. Of course, the first mixture between supernova and GRB was fantastic and expected by the work of Kulkarni, Galama, and others on the GRB 980425 and the supernova 1998. Therefore, GRB and supernova were somewhat related. The second input, which bit by bit became more and more clear, is that before people were always thinking that massive stars would lead naturally, bam, to a black hole, simple. But what it became clear, and now very clear after the observation of the Space Telescope, is that massive stars, under 20 solar masses, are binaries. And therefore it started to surface the idea that the evolution of a very massive star could explain this object, which we studied with Ricardo, with Gursky, in the binary X-ray sources, like SENX3 or even Cygnus X1. But the fundamental contribution, the person who really, in my opinion, gave a fantastic contribution to the study of the evolution of stars, emphasizing the role of a binary system has been Nomoto and his school. He understood the role that two massive stars, the more massive could first evolve, then transfer and then form an object like NX3. And then this object itself could evolve and then what? And then we start to work ourselves that maybe there is a new physics when this star has evolved to the point of having an iron CO core with a neutron star nearby, and we start to work very much in this direction with Grant Matthews and with Chris Fryer. And we introduce, when I mean we, then I will show you the list of the people who have been working on this, but the leader really in this sort of understanding of all this picture has been Orger Ueda. And then we start to understand that there is something magic about the fact that some neutron stars are very close to an iron CO core, and as soon as the supernova explodes, you have accretion. And this accretion can be hypercritical accretion. And therefore, to hypercritical accretion, and then you could have, after the supernova explosion, with a nearby close enough neutron star, reach a black hole. Therefore, neutron star core plus neutron star making a black hole, and then the neutron star, of course, must have created a new neutron star. Therefore, it's a many-body idea. We are in Rome. And in doing this work, I used all the memory of the Rome school. In particular, I read over and over again one of the crucial contributions of Fermi in the beta decay theory. Of course, and you will read in the booklet of the award the memory of Hsien Yang of that work of Fermi discussing with Eugene Wigner. The uniqueness of the considered by Yang the most important paper of Fermi. But I don't want to speak about this here. What I want to speak was the reaction of the Rome school around Fermi. The reaction of Segre, of Pontecorvo, of all the other people of the Via Panisperna, and actually this discussion was already in this physics department. The question was, but where was the proton before? Where was the electron before? Who was the neutrino before the decay? And Fermi explained by second quantization, but this was the difficulty, the major difficulty, conceptual. And the particle physics today is not bothered any longer about this difficulty. You can have, Adone has shown that, a plus, a minus, and then the accelerator in California have studied the psi, and you know that any plus, a minus can go to mu plus, mu minus in a S matrix, which occur in 10 minus 23 seconds. Segre was very intelligent, but he was bothered initially. And of course, now all the particle physics accept this. But what I would like to emphasize is that something very similar, conceptually, is going on now on gamma ray burst. Namely, you have a neutron star, an iron CO core, and this iron CO core interact, and through a classical, not a quantum, a classical procedure, you form a newly born neutron star from the supernova. From the supernova, you form a newly born neutron star, and from the iron CO core, From the iron C core, you form a new neutron star, the leftover, and from the neutron star, which accretes material from the supernova, you form a black hole. And all this does not last 10 minus 23 seconds, which is the characteristic of strong interaction, but lasts only 100 seconds. And this is the novelty. And I'm sure that this will take more than 10 years to be understood by the average astronomer. It's a conceptual difficulty to imagine that a system can transmutate, can change, and understand the beauty and the data from the satellite to follow all this procedure in time. I would like to speak to you about all this in great detail, but I have selected, after the presentation done a moment ago by Marco on the short GRBs, to speak first about the short GRBs and to propose that they are two completely different kind of short GRBs. Both of them originated from neutron-star merger. But this one, as Holger Weda explained yesterday, it can happen that the two neutron stars have a mass smaller than the critical mass. Therefore, the outcome, in addition of gravitational wave eventually, will be a new neutron star with mass smaller than the critical mass. And then reach X-ray optical emission coming out from this new neutron star, massive neutron star. Another case of short GRBs, and this has been a battle to be accepted with a referee, very distinguished, who was one, I think, of the first speaker of our meeting, which finally accepted the idea, is that there are neutron star interacting in time less than 2 seconds and forming a black hole. Therefore, let's see, to give a few examples. The first kind of short GRBs with energy smaller than 10 to the 52, you have the merging and you form a new neutron star. And then you have some continuous emission. These are a typical example. 10 to the 50 erg. This is the short. And this was the afterglow of this short, emphasized in many articles of Nature and so forth. But the characteristic energy of this sort of object is 10 to the 49. Therefore, they have a clean short, less than 1 second, and then here they are missing the data from the XRT. As soon as XRT turned on, you see this afterglow, which can go as far as 10 to the 5, 10 to the 6 second. This is, there are plenty of such short GRBs, but their energy is around 10 to the 49, 10 to the 50, certainly smaller than 10 to the 52. But then there is another object, a neutron star, interacting and forming a black hole. And there is something new here, because it's the first activity of a newly born black hole. What we are seeing is the Kerr-Newman black hole just born of that merging, and the physics is different. There is no long afterglow in the X-ray, and we have modeled the details of that emission that Marco just shown, but you will hear that in some parallel session. We have been able to model the physics with the PGRB and the spectrum the physics of black holes, which we have developed. We have fitted perfectly well this model and found even the interstellar matter distribution, all the details of the short. But what is essential is that after the short is finished, here, there is something new. There is the JEV emission. Therefore, in the short, traditionally short GRB, you never have JEV emission after the burst. In these sources, you have always very large energy of the order of larger than 10 to the 52, 6 times 10 to the 52, 2.8, 2.4, 3.9, and this emission is mainly JEV emission with a very large energy, 10 to the 50. Here you have all the details. We will put this on the web. Okay. Therefore, the key idea is that the manifestation of the newly born black hole is just the JEV emission. And you don't have other activity. You don't have the long afterglow in the X-ray. There is some activity in one case, but in some other cases you don't have. In some cases you don't have even the emission of the JEV, because the black hole must have been a very little rotation, and therefore you don't have this JEV emission. Therefore, this is the first part of my lecture. Now let's go to the following quickly, because I'm afraid otherwise I don't have time. Okay, I manage, but quickly. Let's go to the long GRBs. Okay, the idea of the long, the beauty of the short GRB, I have to emphasize that, is their simplicity. Because you don't have the mess of the supernova around. You have just the pure neutron star. And you can identify when the black hole is born precisely. And you see even in the prompt come in the JEV radiation, what you were mentioning. This is all comprehensible and is simple. The case of a binary with a supernova is much more complex, and this is the reason why so many graduate students in our group are working on this topic. This idea of the collapsing, of the collapser, which was core and the companion, was made possible thanks to the fantastic collaboration in our group with some analytic formula, Chris Fryer with the big Los Alamos computer. But let me just say that the same procedure applies in this case. You can have a neutron star FeCO core interacting, and then from the neutron star form a large neutron star, but not a black hole. And the FeCO core form a new neutron star. Therefore, this is our cosmic matrix for this family 1 with energy smaller than 10 to the 52. There are so many. And here I give you just one example. You see again the same feature at the family 1 short GRBs, but this is family 1 long GRBs. Instead of having a signal 10 seconds, it lasts 100 seconds, and then you have always the same afterglow generated by the massive neutron star, and eventually interacting in a binary with the new neutron star created. This is very similar. Later you can compare this, the family 1, the two family 1. But let's go to the family 2, where the black hole is formed. The first object we understood was 090618. And it's fantastic, the amount of physics which we can do with this system, thanks again to Swift and Fermi. Here you have the neutrons, here you have the supernova, here you have the neutron star. These are idealized diagram. The supernova explode and start to accrete on the neutron star. You have therefore the accretion of the remnants of the ejecta of the supernova on the neutron star until the neutron star becomes so massive as to form a black hole. At that moment, the GRB is emitted. Here it is. And I think this space-time diagram, which we have simplified to the bones, are essential. You have first an episode before the GRB, then the black hole, the GRB, and then from the black hole, you have the JEV emission, exactly like in the other case. Therefore, here you are. The details will be discussed by Wang Yu, by Enderle, by other students, in the most famous case of the supernova 130427A. And again, you can see in these sources, exactly like in the short GRBs, over 10 to the 52, the high energy emission, which is coming out from the newly formed black hole. Therefore, the most delicate point to understand is that while here you have the supernova and the neutron star, here you have episode 1, here you have the GRB, the gamma ray bursts are coming out here. Excuse me, the high energy are coming out here. And therefore this is the space-time diagram in which you see from the newly formed black hole the high energy JEV emission. But let's go on because there is little time. And then there is, in the afterglow of this very high energy gamma ray burst, there is this feature which was introduced by Nusek and Kovaliotou, etc., these three phases of the power law, of the plateau, and this first part. We revised a little bit the paradigm of this because we have a power law phase, a plateau phase, a steep decay phase, and a flare phase. This is new. We are working on this. And we are working on all these aspects in quite a lot of detail, but just some flash on some result. If you look at the power law, these is extremely interesting that if you look at the X-ray in the proper frame, you see that there is some communality between all the afterglow. And there are many technical details which have been explained about possible beaming and some possible change of the power law index. But there is another effect which Muccino has found in our group, that if you take different one of these late X-ray, there is a merging of one in the other one. And this is another phenomena which we are trying to understand theoretically, even in the last hours in our group. And then there is this spike, which is extremely interesting, a new feature. And there are a lot of data about some possible thermal emission in this blue part. Okay, maybe it's better. I don't go much further, but let me at least propose the diagram, the space-time diagram of this process. This is conceptual. You have here the supernova, here you have the companion neutron star, here you have the accretion, you have the GRB emission, you have the high energy emission, But what happens is that when the GRB goes out, there is another part of the GRB not coming toward us in this direction, but going away from us and impacting on the supernova remnant. This is, in our opinion, the origin of the flare. I cannot prove you the details of this, but let's go to the conclusion. Short GRB come from neutron star. There is also a few cases of white dwarf neutron star. They have never a supernova. They form black hole, yes, and they don't form black hole. In that case, they have a hard spectrum, the X-ray afterglow, yes. In the other case, you have high energy, is what I already said. And then on this other case, you have long GRBs, and again, the one below 10 to the 52 don't have a black hole, and the one over 10 to the 52 have a black hole. And again, you have only in this case, the commonality between this family and this family is the presence of the high energy. It's very interesting that these things, this object from here, can start all over, up here. Therefore, you could have this family come to a neutron star, and then you start again the neutron star series, and go on and on. What is the main message I would like to close? Well, there are differences, of course, between our model and the fireball, but that is clear. The traditional approach of considering a GRB as a single astrophysical process described by a time-integrated description was initially justified in view of its short duration of few seconds. With the increase of information in the spectral distribution of the satellite from the ground and from space, the enormous energetic of GRB sources has been evidenced, and then the time-resolved analysis has been possible, and then a much more complex phenomenology has emerged. The essential process of the core, or at the core of a GRB, is the black hole formation. And the black hole formation can be preceded and followed by distinct different astrophysical phenomena, which can be described in the cosmic matrix. And a variety of astrophysical scenarios are describable in each cosmic matrix, involving as in state, like the particle physicist would say, neutron star, supernova, white dwarf neutron star, and as an out state, always the possibility of forming newly born neutron star, newly born black hole, and these different matrices are the beauty of describing all this multifaceted behavior. The necessary but not sufficient condition for the JEV emission is the formation of a newly born black hole. The approach to a black hole, therefore, and then I finish, is different from what it was taught for a long time. It was thought that a massive star would go to a black hole simply. It's not true. It takes place, the formation of a black hole, through a very long path. Each path, each moment is marked by a precise sequence of events. You have first the binary X-ray sources, then all these steps. Each is marked by a different phase of gravitational collapse. As the path proceeds, the influence of general relativity becomes more and more and more pronounced. One finally reaches the birth of the black hole, completely formed in the structure of space-time, at the end of all this family, which I showed before. It is as if nature chose to create a path that only people who can benefit from the knowledge of Einstein's general relativity can recognize. The pauses, the succession of events, the final black holic energy release, and and fully perceive the uniqueness of this cosmic event second only to the birth of the universe.
Thank you, Remo. You are just out 5 minutes of allocated time. Maurice. Wait, Maurice. The microphone coming.
As you know, Swift has also introduced an enrichment of the GRB phenomenology with short GRBs with extended emission. These soft extended emissions and the extended emissions in long GRBs both are along the same curve in the Amati relation. So how is this explained in your proposal, given the very likely origin of short GRBs with extended emission also being from mergers?
The Amati relation is one of the monuments of GRB physics. It must still be understood, and we are working very hard in trying to understand the Amati relation for these systems. The only thing I can say right away is that the short GRBs follow a different Amati relation than the long one. And this is one of the action which we are trying to understand in our model, but certainly need to be understood.
Marco. Wait.
Black hole are a manifestation of the black hole formation.
Marco, excuse me.
So could they come from the jet? You say that the black hole formation implies a jet that could be formed.
For the moment, the result which we are the key point is that the main point is that the JEV emission comes from the black hole in this space-time diagram and not from the GRB as such. And similarly, what we are saying is that the rest of the afterglow comes from this part, which is the collision of the GRB with the supernova. And this is the key point. And then it is very possible, every one of these systems has beaming, and any one of these, from the accretion of the remnant on the neutron star, could have a process of beaming in the normal to the direction of the binary system. And certainly here there could be a beaming process, but not related to the one of the gamma ray burst as such. And similarly, we have evidence that also in this region we have not a beaming but a oblateness, but it's a different one. The way I like to think about is like speaking to the relativist, that before we had a Schwarzschild solution, and then the Kruskal diagram was presented. And we understood that the same solution was corresponding to different realities in the Kruskal diagram. What we are proposing is that it's not one system which explain everything, but are multiple systems, each one characterized by very specific physics, and not overlapping, not the same.
A very short comment and a short answer, please, Remo.
Hello. I'm interested about the scale of the afterglows. So my main point is, as you show, short and long GRBs, the one that formate black holes, They have more or less the same thing, Jeff, emission and afterglow. Why the long scale and the short don't scale? The afterglow. You have any idea?
Excuse me.
Why,
yes, we have.
why only the long scale have this scale?
We have the idea, namely, the only, well, in that diagram, only the high energy is the same phenomena. But in the long, you have the presence of the supernova, which interact with the GRB. In the other case, you don't. Therefore, the uniqueness about the long GRBs, due to the interaction of the GRB and the supernova, are these fantastic scales which Pisani and Muccino and Wang Yu are working on, but only in that case you have the scaling.
So in some sense makes sense that the energy is in some sense stays there and after is released very fast as some turbulence effect, maybe. That is what I think.
Okay, we thank Remo again.